Okay. Good afternoon and welcome to Simon's Electron Microscopy Center's Winter EM course. Today we're winding up our helical modality, and so this is the last of the three structural biology modalities, rather EM modalities that we've been covering. And I think the amazing thing to think about, the same instrument, it's EM, you can do electron tomography, single particle, and helical/2D. Our speaker today is Hernando Sosa from Einstein, and as with many of our speakers, he has practiced many different modalities of EM and structural biology and is an expert of the technique that he'll be presenting today. And something that you should feel free is to interact with him and find what use cases where you can actually use helical in your biological research. And that is the point of this course, that you can interact with this speaker and you can sort of see where you might be focused on one particular modality right now. In the future, you never know what other resources you might need to bring into your research. So Hernando Sosa from Einstein.
Okay, hi. So actually, I may sit down because it feels kind of nice. So you guys had an introduction last week about helical reconstruction. Probably you covered. I'm not exactly how far you went, but actually this would be a good opportunity to, as I talk a lot, to ask questions that you may have been not clear before, or that you want to dig deeper into whatever concept Greg introduced last week, okay? So feel free to interrupt me at any time. Actually, this is urged because this lecture is actually shorter than I used to have it. So I try to focus here just on the basic. I understand most of you here, particularly the ones that are not here, said single part helical reconstruction. I don't care. I'm not gonna use it. It's just single particle. It's kind of interesting historically because it used to be exactly the other way around. And if anything, what is good about helical specimen is that it will help to reinforce some concepts that you will need to know as an image processing in general of images, because we're gonna going all the time back and forth between the Fourier transform, when you use the Fourier transform to analyze your images and what that gives you in order to understand your specimen. Okay, so you know there are many. Helical symmetry is actually very common in biology. Anytime that you have a filament that is formed by a self-assembly process, is most likely or absolutely likely to be a helical specimen. And the ones that we're going to talk are the ones at the bottom, which are large macromolecular complexes. But you know, DNA is a helix, and historically, all the methods that I'm going to talk about come from the analysis, not from the analysis of DNA, but certainly Crick was the one who developed a lot of theory behind, and it has an interesting historical concept that I'm going to touch. So what I was mentioning before, why historically a helical specimen was the first specimen that we got a three-dimensional structure from the EM as a particle, okay? And the reason why was that is going to become obvious, but basically in a helix you see all the views without needing to tilt your specimen. So in principle, with only one specimen, you should be able to obtain a three-dimensional reconstruction. That was realized by Aaron Klug and David DeRosier, and they used that to make a three-dimensional reconstruction of the tobacco mosaic variants that you see in 1968. And historically, EM initially was thought that the only way to get to high resolution was to use very ordered specimens. And helical specimens have this particularly useful property of allowing to get the full three-dimensional view in just one view. So we're going to talk about, you already saw what a helix is, but we just mentioned it, the Fourier transform of a helix, and then we're going to talk about the Fourier Bessel helical 3D reconstruction. We're not going to go into the detail because it's unlikely that any of you are going to use this method. But it's good to know, if anything, for historical reason, and also because it helps you to understand when you see a diffraction pattern of a helix, understand why that is the diffraction pattern of a helix and what information you can get out of it. Okay? If you ever turn out with a helical specimen, most likely you don't, the only thing that you know is this helical, and say, oh, I'm done. Well, you still, whatever method you use, we're gonna need to find what are the parameters of this helix. What is the turn per subunit? What is the rise? And that's something simple enough. It's not. Very complicated, has led to a lot of artifacts, and unless that you're working with a specimen that you know already what it is, let's say an active filament, and even in that case, even if it's a microtubule, you're gonna need to determine that very carefully as you go in whatever method, if it is the Fourier vessel or if it is most likely one single particle method to analyze your filament. So, as you already are familiar, helical symmetry, you just combine these two symmetry elements. You have a rise and a turn per subunit, and that defines your helix. Another complication, you can add also a rotation axis, perpendicular to the axis of the helix, so you can have a 3 or 4 fold helix. But in the simplest, that's what you have: a rise and a turn per subunit, and that's what defines a helix. So there are other terms that you're gonna become familiar with it, which is, okay, the helix is gonna be turning, and at some point you're gonna get exactly to the same subunit. So that defines the repeat, okay? And it's not the same. You have another term here, which is, let me use this, which is the pitch of the helix, which is when you complete a turn here. And as you can see, the repeat and the pitch don't need to be even integers of each other, okay? That's kind of important because, well, now that we know it, that's fine. But you see, the pitch is like an abstract concept that is just is the line that is joining all these points along the helix. Okay, so you have the azimuthal angle, the subunit axial expansion, and you can define the repeat and the pitch. As I said before, a helix, as you see this one, is giving you several views of the same object. And that means that somehow, I mean, they are all superimposing to each other. But in principle, you don't need to rotate the specimen to obtain a three-dimensional view. And the reason that you can think about it, if you already saw 2D crystal, with 2D crystal, you only have one view, and you have to make a tilt series in order to obtain three-dimensional information. We don't have a single particle here, but you build the 3D by orienting all your particles. In the case of helical crystal, a single specimen, you have all the information. And you already have seen the Fourier transform, and you know that equivalent to have projections of your object in all the orientation. If you were to think in Fourier space, what does that mean? Every projection is a section of Fourier space. Okay? So at some point in your reconstruction process, you have fill all your Fourier space with all the sections that you need. When you have a helical specimen, you need to do the same. However, what happened is that for a helical crystal, the intensities all around a particular point in the Fourier space are all the same. So when you take a section in Fourier space, the intensities are all the same. And the phases are predictable, okay? Depending of the number of what we're gonna call the Bessel order, that you don't know what it is, but it's something that when you know what type of helix you have, you know that, then you know how many, all the shifted, how the phase shifted along this line. So there are only two possibilities, depending on what you have a difference of phases here, the 0 either in phase or 180 degrees apart. And the number of times that the phase shift is completely predictable, okay? And that's why you can get a three-dimensional reconstruction, because you get one single diffraction pattern, and you can say, okay, now you know the intensity all in Fourier space, and you also know the phases because they are predictable. So, did you see this type of representation for helices? Okay, that's a radial projection, and as you can see, it's simply, if you take a helix, it's like if you would put every single subunit, and now you open it like in a ship, and now it is represented like that. So here you will have the azimuthal angle from 0 to 360, and here you have the axial displacement. And when you see it in the representation, you see that the helix actually starts to look a little bit like a lattice, okay? So, and they are completely analogous. Well, not completely. There is some analogy, and then we're gonna see what is different. So in principle,
Professor?
yes,
Can you pull back one slide?
yeah.
I'm confused as to what projection is this? What is this projection on?
So imagine that you have a piece of paper. Yeah. So it's actually easier to draw. Let's draw a simple helix here. Okay. So this will be actually be your helix. Okay? In real space. So you can see you have a subunit here, you turn here. So this is your helix. And the projection is you're now gonna take a radial project is gonna take and open this to go from your helix to this. Okay? And the convention is, it could be anyway, but when you have the helical path tilted clockwise, this will be a right-handed helix, and this will be a left-handed helix. Okay? And the reason why it's right-handed is you can remember your finger. When you are pointing up, you are rotating this way. So, what we're going to talk a lot about is how to index the diffraction pattern. And that's analogous of when you index, if you're doing 2D crystal or you are doing 3D crystallography, the first step is to know index your diffraction pattern, know where every reflection comes from. And you're going to do something equivalent for a helix. And you can see that what is interesting is that the same rules apply, because this is actually a radial projection of a more complicated helix. Okay? It's not, you see, not single a subunit going around, but you see a lot of subunits, and this literally looks like a lattice. Okay? And in the same way that lattice planes are going to produce reflections here, lattice planes here are going to produce reflections here. In the same way, the complication of a helical lattice is, again, this is an abstract representation in which I have flattened this out. But in reality, you have kind of the same lattice on the other way, because this goes this way. So in an extreme, you can think about it, about this is like two lattices, one behind another in front. And as a matter of fact, what you're gonna see here are reflections coming from the front lattice and from the back lattice. That are a complication when you are indexing the diffraction pattern, because you're gonna see that sometimes you see a reflection in one side of the diffraction pattern correspond to the front part or the back part. So you have both of them there. So another distinction with absolute 2D helical lattice. You can think about a 2D lattice and think about the Fourier theorem is that you have a lattice with some unit cell here that has been drawn, and then you can think of it as a two-dimensional function or a three-dimensional function, right? And what the Fourier theorems tell you is that you can represent any function as a integral made of sinusoidal functions, okay? And that's what is represented here. You have sinusoidal function going one way and going another, and in the diffraction pattern, the amplitude of each of these sinusoidal waves is going to be a reflection, and the position is going to depend about the distance, the period of that, and so on. So for a 2D lattice, it's the same, but you cannot think about them as just 2D helical wave, 2D waves like here, but they are called helical waves. So it's a bit more complicated. But what happened is that instead of seeing spots in the diffraction pattern, what you're gonna see now is a streak. Okay? It's not just a single spot, but you're gonna see a maximum with a series of subsidiary maximum. And the origin of that is a term that you're gonna see over and over again when you hear about helical diffraction. It's a Bessel function. So, and that's what Crick and Wang and others figured out. What is the theory about what is the Fourier transform of a helical specimen? And if you imagine an ideal infinitely thin turn of a helix, okay, and figure it out, what is the Fourier transform of that? The Fourier transform of that is a series of Bessel functions. So you will have a Bessel order 0 here that will be in the origin of your diffraction pattern. You're going to have a high peak, and then as you go further out, it's like a damper sinusoidal wave. And as you go along the axis of the helix, you get other Bessel's order. So the pattern looks like an X, okay, in which you have a peak at the center and subsidiary peaks coming like that. And before I continue, let's define two other terms. When you see a diffraction pattern of a helix, usually you call the meridian and the equator, okay, these two axes here. So the meridian will be the axis that is parallel with your helical axis, okay? And the equator will be the perpendicular one. So using those terms, the diffraction pattern of a helix, but now this is a continuous helix. This was the diffraction pattern of a single helix. And now when you have a continuous helix, this is the same, is like if you have the convolution with a gamma function where you put one of these terms in every this place, and the effect of that will be to you multiply the transform of this single helix in Fourier space, and now you get what will be the calculated diffraction pattern of a continuous helix. It's still an ideal helix. And what you see is that you have at the origin a big peak because that corresponds to the Bessel order 0, and then you have subsequent Bessel orders as they come along. At the distance between these reflections is going to be inversely proportional to the pitch of your helix. So now let's see more complicated. We don't have just an ideal helix, but a helix of atoms, okay? So this is your continuous helix and real space, and in Fourier space, this is what you have. You have a series of planes or lines that we're gonna call layer lines, okay? But let's say now that you're gonna say, well, I have an atom, an ideal atom, separated by this distance, okay? So this, I can make that by multiplying this function by this function to obtain this function. Still, these are ideal atoms located just at these positions, right? That's the way. So I multiply this ideal continuous helix by this series of ideal planes separated by a distance, which will be whatever distance I choose to put the atoms here. So if I multiply this by this to have this, a multiplication in real space is equivalent to a convolution in Fourier space. So now I'm gonna, the transform of this series of planes here is gonna be lattice points right along the meridian in Fourier space. So this is the transform of this is the transform of this. So if now I convolute the transform of this with this, which is equivalent to put this pattern every this point, now I get this very complicated pattern, okay? And that's how we may understand how the diffraction pattern comes along. A few things to get here immediately is that this is a convolution of this with this. So I put in this big, huge, big peak here, okay? So that's where the big peaks are gonna appear here in the transform. So if I measure this, immediately I know what is the subunit spacing of this helix, which is gonna be the inverse of this distance, because this is real space for reciprocal space, okay? So, to summarize a few things, so now we have a helix in real space, and we subunit axial spacing, and then other distance axial here. We have the repeat, we have the pitch, and we have the radius of this of the helix here. Okay, so when we see it in Fourier space, now we're gonna see a lot of reflection that are gonna be organized. That's the first thing that you realize when you have a diffraction of a helix. You're gonna see a spot. You're gonna see like lines, and we'll see example of that. Lines perpendicular to the equator, and they're gonna be called layer lines. So if you find the minimal distance in which you can find an integral in that you pass all the peaks here, this is going to be the reciprocal of your repeat distance here, okay? The distance between the origin and the first meridional is going to be equal to the inverse of your subunit axial repeat. And the position of this layer line is related to the pitch of the helix, okay? So just by looking at, and that's why I'm starting with the Fourier transform, because if you don't have an idea of what type of helix you have, you probably are going to start by looking at this diffraction pattern, because there is a lot of information there about the periodicity that you're going to use to actually determine the spatial parameters that define your helix. So this is no joke, that's how the structure of DNA was solved. Quite simple. Watson and Crick stole the picture of Rosalind Franklin. They see this huge, nice peak here. They say, oh, that's the subunit spacing. They see the spacing between the layer lines here and say, oh, that is the pitch of the DNA. So now they have all the constraints in which they build their model. And of course, they immediately realized that because Crick was the one who developed the theory to do that. So, because we're not going to use, I'm not going to get into the details of the equation itself, but that's finally how you define the Fourier transform of an atom of a series of atoms. Okay, so this is the Fourier Bessel transform, and if this is the Fourier transform, actually it is better explained in other slides here. So this is the function that we want. It's a real space function. This is the density, okay? And it's in reciprocal coordinate. So C will be the axial coordinate along the axis. Phi will be the azimuthal position, and R will be the radius from the center of the axis. So, but when we do it by Fourier Bessel, when we do it, we go to the diffraction pattern, and we take all these Fourier terms, okay? Which are, this is the reciprocal of the radius, the reciprocal of this, and then the LC is the distance of the layer lines, okay? So these are integers, and this is the C will be the reciprocal of the repeat distance. So that means you're going to have one of these terms for each layer line. And the idea will be, then you do an inverse Bessel Fourier transform to actually obtain this from the diffraction pattern. And in this, what you see, there is this N and L term, okay? So you can see your layer line from your refraction pattern, but what you don't have is this N term. And what is this N term? It's usually called the Bessel order, because that's what it is. It will correspond to the Bessel order of this transform. And what Bessel orders correspond to each layer line is not random. It completely depends and define your helix, okay? And that's what, and is defined by a selection rule. The selection rule, this is the layer line number. This N will be the Bessel order of that particular layer line. Turn is the number of turns that your helix does per repeat, and then the number of units. And as you can see, if you know the number of turns and the number of subunits, you can divide each other, and that's the same as the azimuthal angle and the repeat per subunit, okay? So knowing this and knowing the azimuthal rotation and repeat is the same, okay? And when you know one, you know the other. But sometimes it's easier, even if it's hard to believe, but sometimes it's easier to find out this before the other. Because the problem with the turn per repeat is I just do it more or less. Well, there are many, many helical possibilities. And if you choose the wrong one, even sometimes with an error of 1%, you can be completely in the wrong helical family. And if you are doing trying to do refinement, yeah, you're going to refine your structure to the wrong structure easily.
So can you,
Yeah.
or when you're indexing your layer lines and assigning them a Bessel order, do you take the distance of the layer line from the distance of the first peak of the Bessel order? Or something?
Yeah, Yeah, so we're gonna go more into detail. Yeah, because as I say, the distance from the equator will be proportional to the inverse of the pitch, okay? And the radius, how far they are from the meridian, is related to the radius of what this particular helical feature that is giving rise to that reflection, okay? So, in the traditional helical reconstruction approach, that you can think about as a more what we do, and that from the original paper of David Derros here, we'll go through some step by step, but it was basically you start from a helical specimen, you have your 2D micrograph, and then you want to obtain a Fourier transform of that, because from here is where you're gonna obtain all your Fourier terms to do your Fourier Bessel inversion. So, but the first thing that you do, and if you have never heard the term, but probably is built in all the even the single particle, is something that they used to call it floating. Okay, but basically, because the transform sometimes, and particularly when you have to have a transform which is bigger than your specimen, and at that time there was a requirement that the transform had to be power of 2. That because of the Fourier discrete Fourier transform algorithm that people were using and still is used in many programs. So if you don't float the image, what happens is you will have something like this. So the biggest contrast that you're gonna have is gonna be between the edges of your particle, or where your particle is, and the box. And when you do the transform by that, that's exactly what you're gonna get. You're gonna have a huge reflection in the meridian and the equator coming from the box itself. So to avoid that, you make a box in which you use either the average value of all the pixels here, or the average values of the perimeter that should be very similar. And then you start to see you eliminate that, for example, these strong meridionals here, and that's actually the diffraction pattern of this helical specimen here. That we're there were some filaments were very flexible, so in order to obtain a good diffraction pattern, there was some some of the first image processing to do to make this filament straight. So what they did was you mark the position of the axis, you convert this to the best spline curve, and then you reinterpolate this line to a straight line, and then you obtain a straight filament. Nobody does that. That was the way we do it, but of course that creates a lot of artifacts. One thing we have to be mindful here is that at this time, I mean, you were getting a 20 angstrom resolution. That was great. But there are a lot of artifacts you can imagine when you reinterpolate. There were some areas that are going to be compressed, some areas stretched. But nevertheless, what those also indicate, if your protein itself is very, very flexible, that you really you need to do that even when you select your single particles. If you're doing a single particle approach, you're probably not going to get a lot of resolution because your particles are very distorted. So the straighter your particles, the better. Okay? So anyway, that was the procedure. Straighten the images. Then, for this particular, we find out all the position of the layer lines here, and that's where we started to see what is the spacing between layer lines, to start putting numbers that will tell you what is that selection rule. So, assuming that we already know the selection rule, then the procedure was simple. We get the Fourier transform. This is the diffraction pattern. From this Fourier transform, we measure the intensities along this layer line together with the phases of this particular layer line, and then we do the Fourier Bessel inversion because we know to calculate the map. Okay, so that was the procedure. So this another. So this was an actual example of the software that we used to do it that way. This is the diffraction pattern. This is a microtubule filament. We are marking the position along the axis. That will get straightened. There was a step somewhere in the circuit to actually to correct for the CTF, like in any other model programs and so on. Why so many? Okay. You need a special permission just to see this movie. So, anyway, so here, same procedure. The only thing that I added here is that this is the microtubule. This is the diffraction pattern, and this will be the projection of this of the particular helix that correspond to this microtubule. As you can see, maybe that's a good way to when we talk about the rotation per subunit of the helix, okay, that usually refer what they used to be called the genetic helix. Is you find a helical path that you make sure that goes through every subunit, okay? And that's what defines your helix. However, there are many helical paths, particularly when you have many subunits. So you can see this is a helical path, okay? This is another helical path. And they used to be called like star, okay? Because you see here in the 360, it's not only one, there is another helical path here. So this is a 2-star helix. This one here is actually a 15-star helix, okay? Because you count 1, 2, 3, 4, 5, and when you go to 360, there are 15 of these planes, if you wish to call it. One interesting thing is that this is actually the same as the Bessel order. So, meaning that, for example, there is a 15. There is going to be a layer line corresponding to all these planes that is going to have Bessel order 15, which is in this case is this one here. Okay? Stop me for, you have any question. Yeah.
So there will be a set of layer lines for each start helix that's present in your
Right. In principle, except depending of the mass, the actual object that you have there, some of these peaks will be stronger than others. Okay? As a matter of fact, many layer lines will have very, very little intensity, okay, for that. But the other reason is the strong layer lines are going to be the one with the smaller Bessel orders, okay, because the smaller Bessel order, the higher the peak, and they are going to be also closer to the meridian, okay. So this is like a strong layer line that in this case, this one correspond. They will be the 2-star. Corresponding to the 2-star helix in this case. Bessel order 2. Oh. I can't believe this. Why this?
All the movies are somewhere else.
No, they are in the same folder. But okay, so okay. So that's more all what I'm gonna say about going through the Bessel Fourier. I say, but most likely you're gonna use it, but it's important to know where all the terms come from. A long time ago, we realized that we could use real space methods also to analyze a specimen, and of course they give equivalent results. And in all these single particle or whatever you call it, what you do is you isolate little segment of your filament, and then you use them. It's interesting that when we first started using this method, we didn't use a refinement as you do as a single particle. But if you know your helical parameter, you can slice particles along, and you know what is the turn of each one of them. So you could actually use that information to back project all your volume and get a 3D volume. And we actually use that initially to deal with helical discontinuities, SEMC in the case of microtubules. And that's actually an example of this early effort that we actually saw. You know, you could see the seam because we took very long filament and we have the whole rotation of the protofilaments along and reconstructed using this method. And then we could actually, we found that within it we have not one but many helical discontinuity depending on the filament. This is one of the first in which they started to use iteration to actually refine. You obtain a model, and then you use the model to refine the helical parameter, the turn, and the rise per subunit around the reconstruction. I would say depend, but in our hands, you always need to know the helical. It was thought that you could actually put like a cylinder there, and somehow the method will converge to the helical specimen that you have. I found that that's not the case, except if you have a very simple helix that you almost can recognize it by eye because you see. But when you have a complicated helix with many subunits superimposing, like a microtubule or a membrane that forms a tube, usually these are complicated helices that are harder to index properly. So this is another method that was used to obtain the structure of the microtubules. Here again, they use the single boxes, and then they refine the orientation of these boxes to obtain a reconstruction of, in that case, what was grade 8 angstrom resolution map. So going back, and now we're going to spend more time about exactly the parameter, is that whatever you do, and most likely you're going to use rely on or any other method to do, it's good to have a very good idea what is your helix, okay? So that's what we're going to spend some time doing. Assuming that you have no idea what it is, that's what you're going to face. So you have something that, okay, it's a filament, most likely it's a helix, then you do a diffraction pattern of your images. And then you see, if you're lucky, you're going to start to see a layer line. Of course, this is a computer calculated pattern, so it looks beautiful. In reality, it's going to be much less beautiful. Part of it because you're not going to have one long straight filament that in your specimen, but you get the idea. You're going to see a diffraction pattern. So your question is, okay, how can I use that to determine what type of helix I have here? So again, let's go back to selection rule. So the selection rule, one way to think about it, or how many units you have per turn. So in this case, we have 13 subunits in 6 turns. Okay? If you count the number of subunits, 1, 2, 3, 4, 5, if you go up to here, they're going to be 13. Okay? And you have 6 turns. But 6 turns of one particular helical path. You have 7 of another particular depending which way you go. But with the 6th turn, you're gonna go through every single point. So that's why it's a good helix to choose from. Actually, you go for every single point if you go in the other direction for that particular helix, which is acting. So, again, the selection, so this is the layer line number. This is the number of turns and number of units per repeat. N is the Bessel order, and M is just an integer. So, what the selection rule say is that you're only gonna find layer lines in positions that are gonna satisfy this equation, okay? So, there are no perfect helices, okay? There are always a little bit, you're not gonna find exactly, let's say 13 units in 6 turns, but maybe it's more like 14 in 12 turns. So it's almost the same, but not exactly. So a real equation that just the height of the layer line as a real number and not an integer is this one, where C will be the position along the meridian, okay, of the layer line. N is still the Bessel order. Phi will be the twist angle or the azimuth. I apologize, in some of my slides I use phi, and here is omega, but it's the twist angle, it's the angle of the H will be the subunit spacing, M will be the same integer. So then you have so these two equations are sort of equivalent. I like still to use that for historical reason, but also because you always find numbers that would approximate this very good, and it's very easy to go from here to actually the number of subunits per turn. So that's actually what I use sometimes when I want to find what would be the perfect definition of my helix. So, and remind about this distance. Okay, so any question about this? So you're going to see some examples of that. So, this is the selection rule. So you can write a little Python code or whatever you feel like it, and then see exactly what are, if I give you that, you're gonna see a layer line 0, of course you get 0, but you can see what are all the Bessel orders that correspond to each of these layer lines, okay? So if that would be, for all these layer lines, that will be the Bessel order. For some layer lines, you see that there are 2 overlapping Bessel orders, but usually, I mean, because the second Bessel order is going to be further away, you can just consider the first one when you are doing the indexing, okay? As you go to higher resolution, you're going to see more and more layer lines in some of these. Bessel order. So, the trick here, why that allows us to go back to the selection rule, is that we see this layer line. Of course, I am giving you the selection rule to start with, but that's actually what we need to get. Okay? So, we have the diffraction pattern. So, we start to think, well, how can we index this diffraction pattern? Well, one trick will be to do what is called an NC plot. As I explained before, the diffraction pattern of a helix is analogous to the diffraction pattern of a lattice, okay? And the reciprocal lattice will be this NC plot, in which you're gonna plot the height of the layer line here, okay? And then the end value. So the idea is, you have your diffraction pattern, and you're gonna assign each peak to one peak on these layer lines. Okay, so that's what you need to do. Okay, maybe I skip that now. So, but the thing that you have to remember when you do this NC plot is that you have a superposition of the back and the front of the helix, and you can see this in this example. Here, computationally, I sliced this filament to put the front or the back. So this will be the diffraction pattern of just the front or the back. So that will be, if I'm going to do the NC plot, I will do it only with this. But of course you have these two of this mix, so you have to kind of, by trial and error, if you put it in the wrong one, you realize that you cannot get a lattice, that you don't get all the point falling, the layer line falling into a lattice. Of course, that can get complicated, and it's not just in this lecture that is complicated. Sometimes you have this has been always the problem with helices when you don't know it, and getting it wrong is not impossible, particularly because these are not dots, these are just streaks. So where do you put this lattice point? Here, here, or here? So it's not obvious. So when you start to do it, the first thing that you have to do is, well, at least the height has to be right. So you have to find a lattice in which you can see nicely all the points intersect, all the major points being intersected by points in your lattice. And of course, there's gonna be a lattice which will be the backside, which also will fit the other point. But of course, you can get it confused because there are points back and forth, you don't know which one is what, and you can get a wrong lattice. And then you can see that sometimes, for example, here, you have this layer line here, major layer line, in which no lattice points are going through it. Okay? This is another example. This is a microtubule, and this will be the L versus N plot. Okay, so that but when you and in blue, I was putting the point that you would expect also by the lattice in the backside. So, some important to start assigning Bessel order. Well, when you do the unit vectors, if you know the size of the subunit, you know that the dimension of the unit should be approximately equal to the inverse subunit dimension of the main vectors of your reciprocal lattice. Okay, and this one is actually another one that is quite useful, because if you know because you're gonna see the radius of your helix. Okay, that's something you measure in your micrograph. Okay, and the value of n of each layer line is approximately equal to to this equation. So it's proportional to P R, capital R. R will be the the radius would be the distance to the meridian, okay, in the reciprocal space. R will be the radius of your helix, okay? And then when you see every line line, you see this line line is likely to be 2 or 3 or 4 you get by this number. But then there is another rule that is you're gonna get two numbers very close. Okay, it's a 2 or it's a 3. Well, if one way to do it is the n is odd or is even, depending if you can do it in the Fourier transform. If you look the faces of the point, if they are odd, if they are in phase or they are separated by 180 degrees. Another, that's one way to say it. Another more simple way to see it is when you see a helix, okay, you're gonna see if the helix is centrosymmetric, right? That means this side is identical to this side, okay? Well, that's an even case, okay? So the liar lines are probably gonna be even because that's a centrosymmetric structure, okay? And the faces, if you were to measure it and convince yourself, once that you have your helix aligned, you're gonna see that the phase difference between this point and the equivalent peak is gonna be either 0 or 180 degrees. If it is centrosymmetric, it's gonna be even, and it's gonna be 0. And okay, the other is the sign. So depending on the hand of the helical path, you assign the sign of n. So it could be you have the 2 or the -2 depending if the helical path is left-handed or left-handed. So that's something that okay, I'm gonna skip this. So the convention n is positive for right-handed helix and left-handed for. So you cannot determine the hand just by a single micrograph. Okay, so there are ways to do it. One way would be you can shadow your specimen, and if you keep track of everything, you can say, oh, I'm looking at some helical paths here, okay, or here, and I can see that these are left-handed. I'm seeing from the top, the surface of the top, so I can see that that will be, if I go this, the helix go left, so this is a left-handed helix. Another trick that you could do is you can make a tilt. I mean, you only need to do this with a few specimens. You don't have to do it to every 3 reconstruction. Once that you determine what type of helix you have, you're done. You do whatever procedure you have. So this is only that you do one. So another thing that you tilt your specimen. If you keep track, you notice this sort of thing. Here you see a left-handed helix, and you see that if I turn it this way, this side become fuzzy, and this become kind of sharper, okay? And if I tilt the other way, it's actually the opposite, okay? And if you would have a right-handed helix, it would be the other way around, okay? So here is the projection. You see like this helical path, when they go on the edges of the helix, you can see them clearly. But when I tilt it, this becomes fuzzy and this becomes very sharp, okay? So that will tell you. Of course, you don't have that in the image. That will be your first. You do this experiment and say, aha, we have a left-handed helix here, and if you see this distance, you also know the pitch, so you know where that helix is going to appear in your diffraction pattern, and you can see the radius here, so you know approximately what Bessel order should be. What else you know? You know that if I trace a line here, okay, but in this case it's not that clear, but you will see that it's not exactly centrosymmetric. So it will have to be, and no, actually this is centrosymmetric, you see it here, but so that will correspond to a even Bessel order. This tilting also, you can mix it with the diffraction pattern, and actually you're gonna see when you tilt it is that some spots are gonna become stronger at this layer line. So you are actually, you will identify this Bessel order right there on your diffraction pattern. And if you know the direction of tilt, you know, oh, I know that these are positive n, and then that will help you to determine the n. So you do this, you don't have to do this for every single layer line. You have a selection rule that has to fit. So the point is, if you actually find for two layer lines, sometimes only for two layer lines, which are not orders of each other. When I mean order of each other, is you have layer line 1, let's say, layer line 1, Bessel order 2, and then you're going to have another one which will be 2, layer line 2, and then Bessel order 4. These are the same order, so they have the same information. But if you have like vectors going in different directions, like one is a layer line 15, layer line 1, and layer line, I don't know, 23, which is -2, you have two layer lines there. You can now use these two different layer lines to actually find the selection rule, okay? Because it's like a system of equation. I mean, not exactly right, but I myself wrote a script to go through Python to go through several possible selection rules in which they will satisfy this number for these two layer lines, and that gave me the selection rule of that. So we're almost done. So resolution criteria, as everybody uses now, most people use for is you divide, you calculate two maps and do a Fourier shell correlation at the end with all the goods and bad that a Fourier shell correlation does. Another, in the old days, but still useful because that tells you how far the resolution is. You can see how the phases in the highest resolution layer line match to each other. When you do an average of different filaments, you're going to have slightly different phases in all. If it is just random, they will be all over the place. When you see that the phases matches and you go to the highest and higher resolution, that will be an indication of the resolution of your map. Software. So everybody now is using Reliant and single particle, and Reliant has a plugin to do helical reconstruction, and that's fine. That works well. Maybe because I come from the old times, but we use our own series of methods, which are use a little bit of everything. Okay. And the only thing that I can say is that when you understand your system, I find it much better because we can really tweak it to the specimen that we have. There are some characteristics of helical reconstruction that are unique. It's not just a single particle problem, because one common problem is that the spacing between subunits sometimes becomes very, very small. For example, in the case of microtubule, it's only 5 angstrom. Okay? That means the subunit is only 5 angstrom. So ideally, you will separate your single particles every 5 angstrom to take one is different. But of course, when you do the refinement, the thing is going to find it, and it's going to fall into the one of the previous one. Okay? Because it's only 5 angstrom, that depending on it could be 2 or 3 pixels only. And then, you are aligning, and then you are aligning that your single particle set, half of it is just the same particle, because sometimes it just comes down and when it's try to refine. So you have to adjust for these sort of things. Okay, so that's something to keep in mind. And different software do it differently, and we do it in on our own way too. Okay, and we have got some pretty good resolution. I think we attribute it to some tweaking that we have done for the microtubule filament that we have, and I will talk about what we actually do. Yes.
When you have that case, would it be equivalent to thinking about if you just double the rise and double the rotation, it'll give you the same helix accepts?
You could do that. Yeah, I mean, yeah, you definitely could do that, but you may lose information. Okay, when you do that, but yeah, that's the kind of thing that you think about it. The other thing that when you do helical reconstruction, because we do microtubule, we can apply the symmetry that we want. We for example, we can choose a helical path, the ideal helical path that goes through every single subunit. Okay, but we may say we may have a seam. So then instead of that, we saw one that goes along a protofilament. So we treat the whole microtubule as if it would be my asymmetric unit. Instead of being one tubulin, is just the 13, let's say 13 tubulin that make like a little log washer, and then that repeat with the pitch of the microtubule. So you could actually adjust all that in your for any helix, and depending on the problem that you could adjust it that way. So, I mean, the workflow that we pick the filaments, we mark the axis, and that we actually do it iteratively. Ideally, what we would like to find is the coordinates of the axis, so that we don't have to shift or do anything during the refinement, because we are exactly in the center of the helix, and the only thing that we will have to find is what is the rotational, the azimuthal rotation of that particular. In practice, we always back and forth. We have to align a little bit the filament. So, because it's a refinement, we start with a low resolution model. One of the advantages of the Bessel reconstruction method is that you never use a model. The structure that you get initially is just based on you assign your symmetry, and that the structure that we have. And we actually at the beginning we used that as our initial model. Our low resolution model came from helical reconstruction, so we have any possible bias. In practice, if you started with a low resolution model, and now that we go to atomic resolution, that you have the truth test, if you don't see secondary structure, you know that you screw it up somewhere. I mean, probably you have the wrong helical symmetry or something. But if you start to see, you started with a model at 20, 30 angstrom, and you start to recover secondary structure, you know that you are in the right path. So then we classify filament. Is in our case that we work with microtubule, there are microtubule with 11, 13, 14, 15 protofilament, some with seams, some with. So we find a first step of classify the filament. That will be the same, for example, if you do helical tubes made of membrane are going to have different diameters, maybe different helical symmetry. So you can run a first step just to classify for a homogeneous set. Then you determine the helical symmetry of these. I used to do it just by looking at the diffraction pattern of a few of them, and that define, okay, the symmetry is more, and then let it refine with one of these programs. But I know for a fact if you started with the wrong one, the refinement just locked into the wrong symmetry. So you have to have this pretty close. Just try the single particle boxes. then you determine. So we usually do a first run, a 3D reconstruction, and for example, we do that with the spiders. At this point, we get a reconstruction at about 10 or 8 angstrom, okay? And then we use that as a refinement step, and we use that either using rely on or free align on the refinement. And we somehow have a iterative process in which actually we go back to actually even to the classification of the filament with a better map that we obtain on this at this step. And then at the end, as in any other or single particle or cryo method, at the end we just go, once that you get 3-4 angstrom resolution map, we do or model building with a common tool that everybody in Crystal could, Phoenix, or in most cases, because you already have a model of the structure, we use modeler or to actually to build a structure based on some other structure, and then we just refine it with Phoenix and CUT. Yes.
What particle box size do you use? Like specifically like the distance or what your subunit?
Right. Well, that will depend on your helix. Okay. So to give you an example, we work with microtubule. So they are about 400. I mean, we used to with a big array, not just a microtubule, with kinesin and with some other stuff. So the diameter could be 50 nanometers. Okay. The distance of the subunit between along the protofilament is 80 angstrom, more or less, in any microtubule. But the distance between subunit is 5 angstrom, as I said before. So we use a box size. Actually, we use every 80 angstrom. Okay. So there is a lot of overlap between the boxes. So we use 8 angstrom and the size. So we use and maybe the equivalent of 600 by 600 angstrom. Okay. So that there, you haven't done a reconstruction. I'll tell you why we are using, for example, some programs and other. Relion is great, but you have to put the whole particle in your GPU. Okay? So if you have a huge particle, that's a problem. You have to do a lot of binning to put it there. So, so that's what we are using Freeline. I mean, we tested the two and we were in similar resolution during the refinement. And the other advantage is that we can run a lot of reconstruction, try different things, and check if that is giving us a better resolution or not. But anyway, but that's the size. So you can get, I mean, the pixel size that we are using now is about 1 angstrom per pixel, actually less, 0.8. So that means like more than 600 by 600 pixel size boxes, which is relatively big. For the, yeah.
So this is a question from YouTube. So one of the students asked, what will be the validity proof that you're refining the structure and not making up one? So I guess something like
Yeah.
Yeah.
So, I mean, that has happened, and they have been papers, but that was particular during the blobology time, because all these reconstruction, even they were even below 10. Okay, so you will get something that look reasonable and say it's great, but you know, if the structure, as I say, doesn't, you don't see secondary structure and it getting better as the refinement goes, probably you have the wrong symmetry. And there are many reasons to having the wrong symmetry. Historically, one of them is, and sometimes the liar lines, when you see the diffraction pattern, the off-meridional one, are so close to the meridian that they look like a meridional. Particularly the specimen is a little bit tilted, okay? So then some people say, oh, that's a meridional, that's the subunit spacing, and then they get the whole symmetry wrong, okay? But there is a case like that, and then when they started to get the structure. They couldn't pass certain resolution. Even though in the diffraction pattern you could see layer lines going up to high resolution, but the refinement didn't improve. So that's a symptom that you may have it wrong. And certainly there is nothing wrong in try, if you are not sure, try a few ones, okay, and then see the one that actually works. Because it could be that you have two alternatives and you're not absolutely sure because your initial data is not that good to actually, because you're trying to define the symmetry with only one specimen. So you need to have the right one to bootstrap you into the right one. Yeah.
That's right.
Yeah. So here are some, examples that you have seen. So this is actually probably the highest resolution that was solved using just strictly Fourier Bessel reconstruction. But one thing that you realize here is that to get that, it was not just a simple Fourier Bessel program that I described. They have a lot of corrections in that to correct for different filament diameters, all type of disorder, so that they incorporate here to get to that resolution. And at least in my experience, it's a lot easier to incorporate those corrections in real space, and which is basically what all the programs do. When you are slicing your filament in single particle, if the filament diameter changes, you can just throw it out. You may have enough particle of the right diameter, or you can select for them, and you can correct for out of plane tilt quite easily, and this sort of thing. Yeah. And as you can see, now you can get two pretty. I mean, I think the high. I think the short circuit now got some of the tough filament at 2 point something angstrom. I mean, at this resolution, I'm gonna be honest, sometimes 3.4, 3.7, and even 2.9. I mean, I have seen 2.9. I will say that if you say that you have 2.x resolution, you gotta see almost the hole in the rings of your aromatic residues. And I hardly ever see that in a lot of structure. But certainly below 4 angstrom, you see almost all the side chain. You're gonna make up what is the right rotamer and so on. So yeah.
If you were like interested in looking at the interaction with protein would you use this reconstruction method?
But that's what we use. So yes. yeah. So that all these were done. I mean that's from our lab. These I mean, to study kinesin or myosin with actin, I would say that's the ideal technique. I mean that's the natural substrate. That's where the protein generate force. That's what they do. So you actually can see them interacting with the microtubule. Which I mean, there are a lot of crystal structure of, but interacting with the filament is usually that will be the only way. And also, with a tau filament, anything that biological is a filament, probably the natural way to analyze it would be with some sort of helical reconstruction method. Yeah.
Do most of those reconstructions utilize in-house custom scripts, or would you be able to do that with like out-of-the-box free line IHRS?
Well, I think that's definitely very, very, in-house. You can ask. I don't think you can even get actually the exact method of that, or maybe you have it here, don't you? Yeah. No.
I doubt it.
Yeah. I mean, I know David Stokes used it for a while, so he may have it, but I wouldn't go. I personally wouldn't go. It's too complicated to try to untangle the method now. I mean, rely on, I probably try first with rely on. I think Greg is using rely on he has his own custom method to analyze microtubule. He said that he's using rely on to get actomyosin map, probably also in this range. So probably that would be a good way to start to do it. Free align, if you ever use free align also has a module to deal with helical reconstruction. It's a little bit more custom, so we do all the analysis previous to get to free align with our custom program, which don't do anything particularly fancy, except there are some steps that we have done to make sure that the helical symmetry that we have and the helical symmetry that we get at the refinement match each other. And I think we have improved the resolution, but actually we know that we have tweaked the map to increase the resolution. But if you have good data, I would say you just try relying the first time. Probably you should be able to get to as long as you know your symmetry of your specimen. Because I think you have to input that also in rely on first. I don't think there is any program that is gonna magically refine to the right symmetry. So here, I mean, a few. So here is where sort, describe, rely on. More theoretical one, if you want to see, there was a relatively recent paper by Ruben Diaz and David Stokes, where they describe their Fourier Bessel reconstruction method. I mean, it's good to see, to go over what I just say about the layer line, the origin of the Bessel reconstruction, even if you are not going to use the Bessel reconstruction per se. Egelman, most people use some form, or even, actually we have one part in our algorithm that use routines from the Egelman reconstruction algorithms to refine the helical parameters. And yeah, that will be the paper that I will. And this, of course, David de Rosier is the one who invented all these Bessel. So David de Rosier will be like the creek of helical reconstruction in the case of EM. So questions or more questions? That will be it.
Thank you.
No, you're welcome. So anyway, any question, feel free to send me an email.
We'll get the slides from Fernando right now.
Yes,